In this session of ray optics, we learn the typical light rays what we use to trace the image for lens. Say, first light ray is parallel, say what I marked as 1, from object AB, parallel to the principal axis. After refraction, it passes through principal focus. That is the first ray. Second ray is the light ray passing straight through the optic center, this one. Third ray is the light ray which passes through the focus first and then falling on the lens, which becomes parallel. So these are the three different light rays what we use typically to trace the image in case of lenses. So now we learn to derive the lens formula, that is a formula which connects focal length of the lens, object distance and image distance. Even though it is not straight away given in the NCERT textbook, but they have given it as an assignment in the textbook in the main part itself. Now we start with that derivation. It's a simple derivation, just like what we did in case of mirror, that this follows. I start with the figure again. Say, I write a figure here. Just observe, we write a simple figure. Say this is the principal axis and I write a lens there like this. Now we consider two light rays, F here focal length, principal focus, and this principal focus. I extend this slightly this way. Now I write the object slightly beyond, say F like this, AB, I call that as object. Now the light rays we write to form the image there. Say one light ray parallel to the principal axis like this. After that, as we know, it passes through the principal focus. Now another light ray what I take is to pass through the optic center straight away like this. Say this is the optic center. Say right like this. These two are enough for us to go for the derivation, and we write the arrow mark here and we write the image of the object at this point. It's an inverted image. Say A dash, B dash. And we write down all the distances from the optic center. This is the optic center O. Then this distance, object to optic center, is U. Object to image is V. And object to focus is focal length F. Now we mark this point on the lens as M and we join M and O there like this. Now we start writing like this. Just observe, in the similar triangles ABO and A dash B dash O, say we write from similar triangles, first pair is ABO and A dash B dash O. We write A dash B dash by AB, which is equal to BO, say B dash O divided by BO. That is A dash B dash by AB, which is equal to B dash O is V, BO is U. This is our equation 1. Now we write another pair of similar triangles. that is, say, MOF and A dash B dash F, A dash B dash F. We write A dash B dash by MO, which is equal to B dash F by OF, which we can write as MO is equal to AB. I can simply write A dash B dash by AB equals B dash F. B dash F we can write from figure V minus F by OF is F. So this is equation 2. Observe here, MO, here itself we can write MO is equal to AB. In the figure we have used that. Now from equation 1 and 2 we can write, from 1 and 2 we can write V by U equals V minus F by F. Say if we simplify this, we will get the final relation. We do that simplification. Say I take this V onto this side, 1 by U equals V by Vf minus F by Vf, where I can cancel this, where I can cancel this. So 1 by U equals 1 by F minus 1 by V. So after rearranging the terms, I get 1 by F equals 1 by V plus 1 by U. Now by sign convention, U is negative, V positive, F is also positive for convex lens. Therefore, I can write 1 by F equals 1 by V minus 1 by U. This is what we call as lens formula. Say this is very similar to the one what we arrived for the mirror. Just learn this. So 1 by F equals 1 by V minus 1 by U. This is the formula what we call as lens formula. I just go through it once again. Say we have taken two rays to trace this image. One from the object parallel to the principal axis, that is AM, and another, say, straight light ray passing through the optic center, what I have marked in green. Now this creates two pairs of similar triangles. One is ABO, A dash B dash O, and another pair is MOF and A dash B dash F. So in ABO and A dash B dash O, I can write A dash B dash by AB, that is A dash B dash by AB. B dash O, this distance by OB or BO. And A dash B dash by AB, as B dash O is V, I have substituted. BO is U, I substituted and I get relation 1. Now, for the sake of second pair of similar triangles, MOF and A dash B dash F, we write A dash B dash by MO equals B dash F by OF. A dash B dash by AB, as MO is equal to AB there, as red line what I marked is parallel to the principal axis. Then we have A dash B dash by AB equals V minus F by F, because B dash F is V minus F and OF is F. So from 1 and 2, as left hand sides are equal, right hand sides must be equal. V by U equals V minus F by F. We take V onto this side and separate the denominator. We get 1 by U equals 1 by F minus 1 by V. But transferring this onto that side, V onto this side, 1 by V plus 1 by U, we get sign convention. By sign convention, we get U negative, V positive, F negative. So we have 1 by F equals 1 by V minus 1 by U. This equation, even though we have derived it for convex lens, it is also true for concave lens. Now, with this idea, we proceed on to next concept. Say, the next concept is, we just think of like this. Say, what is the major use of lens? Basically, lenses are used to bend the light ray. Therefore, now our idea is, what is the ability of a lens to bend the light ray or deviate the light ray from its path. That ability is what we call as power of lens. So now our concept is to learn the power of lens. That means ability of the lens to bend the light ray. That we learn now in the form of a technical definition. For that, I write a figure here. Say this is the principal axis. I write a lens there as usual. Say this is the lens and this is the principal focus and this is the principal focus. I write a parallel beam of light ray to fall on the lens like this. And observe, I extend this line to show the path when there is no lens. So once it is there, now refracted beam passes through the focus like this. This is the refracted beam. This is the incident beam. This dotted line indicates the incident ray path if there is no lens. So with this, now we think of this angle. This is delta, what I call, and this is also delta because they are alternate angles. Now we join this point in the lens to the optic center. We call this as O and this height as h. Using this, we can define the power of lens, but this distance, as you know, the focal length, that is optic center to the focus. Now, power of lens, how to define it? Observe, we write tan theta for this. Tan delta I write. Tan delta is h by f. For h equals 1, tan delta equals 1 by f. This is called as power of lens. This tan delta is what we call as power of lens. 1 by f. So what is the definition now? Power of lens is the tangent of the angle by which it converges or diverges a beam of light when it falls at a unit distance from the optic center. Let me repeat it. Power of lens is the tangent of the angle by which the light ray diverges or converges when it falls at a unit height from the optic center. That is the definition of power of lens. Let us write down that. Power of lens is tangent of the angle by which it converges or diverges a beam of light when it falls at unit distance from optic center. Optic center. This is the definition of power of lens. Let us go through it. Power of lens is the tangent of the angle by which it converges or diverges a beam of light which it falls at unit distance from optic center. So this is what we call as power of light. And we learn now, why do we call it as power of light physically? In fact, power of lens, because we know, as we said in the beginning of definition of power of lens. It is the ability of the lens to deviate the light ray. Now we write, say, the figure for two lenses whose focal lengths are smaller or bigger. We just write down. We write first lens like this, and here a beam of light. This is the focus, and we say its focal length is 5 centimeter. This is 5 centimeter. Now I write another figure where the lens is having more focal length, that is around 15 centimeter. We write the parallel light beam again, but as its focal length is larger, it bends to the large or converges at a distant point like this. This is, say, 15 centimeter, if focal length is 15 centimeter. Say, observe, here in the case of first lens L1, the light beam bends much to converge to a point at 5 centimeter. In the case of second lens here L2, the light beam bends little bit less to converge to a point at a 15 centimeter. That means bending is more when the focal length is less. Bending is less when the focal length is large. That's what we got. Say tan delta is 1 by f what we got. Say, as it is clear from this figure, focal length is less means power is large. It is bending more. If focal length is more, it bends less, so power is less. Therefore, the idea of power physically is how much it bends. So, smaller the focal length, more is the power. Larger the focal length, less is the power. Now, if focal length f is expressed in meter, then the power of lens is measured P. The power of lens P is measured in diopters. Diopter, and symbol is capital D. So diopter is the unit of power in SI system. So what is 1 diopter? Power of a lens is said to be 1 diopter when its focal length is 1 meter. Observe, to say power in diopter, one must write focal length in centimeter. Therefore, power of lens is said to be 1 diopter when its focal length is 1 meter. Many students make mistakes, say, when calculating the power without converting the focal length into meter, because many times in the numericals they give it in centimeter or in other unit. To write it in diopters, one must convert focal length into meters only. That's a very important thing now. So with these basic definitions of power of lens and its relation to focal length, we now straight away go for another derivation where we learn what we call as combination of lenses. What do you mean by combination? Say, in a project work what you are supposed to take, you are supposed to build up a telescope. For that you require, say, 10 centimeter focal length lens, convex lens. You go to a lens vendor and you ask him to give you 10 centimeter focal length lens. At present, he says, at present I don't have one 10 centimeter lens, but since you are doing a project on lens, telescope, you all know, say, about the lenses, therefore I will give you two 20 centimeter focal length lenses. You know how to use it as 10 centimeter lens. Now, how it is possible to use a 20 centimeter lens as a 10 centimeter lens? That's what we want to learn. That is where the combination comes to our help. Now we start learning the combination of lenses. Say, we start thinking of like this. Say, we write the figure first And then we start thinking of the derivation and some definitions also. Say this is the principal axis. There I write two thin convex lenses which are in contact. Two thin convex lenses which are in contact. Say like this, they are in the contact with each other. This I call as L2, this I call as L1. Now, the L1 has the focal length f1, L2 has the focal length f2. We want to derive relation connecting f1 and f2. But what we get in that relation, say, as that vendor says, we can make use of two 20 centimeter focal length lenses as a single 10 centimeter lens. That means we can replace two lenses by a single lens. Then that lens focal length is called as equivalent focal length, and that lens is called as equivalent lens. So now, what is equivalent lens? Equivalent lens is that single lens which produces the same effect as that of the combination. So that means, what do we mean by same effect as that of the combination? Say if this two lenses for, say, the object distance of u 10 centimeter produces an image at 20 centimeter, then that is called as the effect. We can take a single lens which also produces an object at 20 centimeter when the object is at 10 centimeter. So that single lens is what we call as equivalent lens, and its focal length is called as effective focal length or equivalent focal length. Now we are going to derive an expression for effective focal length of this combination. For that we write a diagram. Just observe, I consider only, say, one beam of light ray like this. This is the light ray. Once it falls on L1, it bends once like this. And once it comes out of the L2, it bends once again to form an image like this. Say here, this is the image, what I call as I, and this is the object, what I call as O. Now to derive expression for equivalent focal length, I use the formula, lens formula, 1 by f equals 1 by v minus 1 by u, what we have just now derived. For this, what I do, I consider L1 first and then L2. So just like what we did in case of lens maker's formula. There we considered one phase first, later on second phase. Here also, one lens first and then second lens, L2. So for that, only one lens L1 is there, means the second refraction will not be there, second bending will not be there. It used to form the image I dash there. I dash is the image formed by L1 only. At a distance, I take it as V dash, and final image V at, final image I is at V, and object is at U, like this. As we have taken thin lenses, small distance variations in the optic centers and touching point can be neglected. Now we start proving it. Say, only when L1 is considered, when L1 is considered, what we have, 1 by f1 focal length of the first lens is equal to 1 by v dash, because I dash is the our image for that, minus 1 by u. This is our first equation. Now, as we did in that derivation of lens maker's formula, here also this I dash acts as an object for the second lens to produce the final image I at V. So, I dash acts as object for L2, second lens L2, to form final image final image at I. So we now have, as I dash acts as object, U can be replaced by V dash and V is V, F is F2 now. So applying that, 1 by F2 equals 1 by, say, V minus 1 by V dash. So this is our second equation. From 1 and 2, we can, by adding the two things, we get the final relation there. Therefore, adding 1 and 2, we get 1 by F1 plus 1 by F2 equals 1 by V minus 1 by U. But observe, as we said in the beginning of this derivation, we can replace this combination of two lenses by a single lens, and I write the figure for that. Just observe. This is that single lens with the focal length F or F equivalent EQ. Now this produces an image like this. Say I write this is O, this is I, and this is V, this is U. For this we write the lens formula again. Observe here, single lens whose focal length is F equivalent. EQ stands for equivalent. Simply sometimes we write F only. We write 1 by F equivalent equals 1 by V minus 1 by U. From the definition of equivalent lens, that is, it is the one which produces same effect as that of the combination. V and U should remain same. Therefore, from this equation and this equation, we may call it as 3 and this is 4. From 3 and 4, from equation 3 and 4, we write 1 by F equivalent is 1 by F1 plus 1 by F2. So this is called as the formula for effective focal length of two thin lenses when kept in contact. When they are not in contact, we have other formula, but for the time being, we learn what is the formula for effective focal length when they are kept in contact. So this is the derivation. We just go through it once again. Say we consider two thin lenses L1 and L2 here, and L1 focal length is F1, L2 focal length is F2. I have an object O and one light ray coming from that falls on L1. Once it undergoes refraction in L1 to fall on L2, there also it undergoes one refraction to form the final image I at V. But to derive the equivalent lens formula, that is the single lens which can produce same effect as that of this combination, I use 1 by F equals 1 by V minus 1 by U. To use this, what we do is, first we consider only lens L1. That is, only one lens is there, means at this point, once it bends at L1, the second lens, as it is not there, it simply travels to form the I dash image at V dash. Therefore, I can use the lens equation 1 by F1 equals 1 by V dash minus 1 by U, because V dash is the image distance. Now, this I dash acts as an object for the second lens L2 to form final image I at distance V. Therefore, we can replace U in the lens formula by V dash now, because I dash is the object, V as V only, F as F2. So I get 1 by F2 equals V, 1 by V minus 1 by V dash. That's our second equation. Now we add 1 and 2, we get 1 by F1 plus 1 by F2 equals 1 by V minus 1 by U. We call it as equation 3. But this combination can be replaced by a single lens whose focal length is F equivalent, which also produces same effect as that of the combination. That means when you keep the object U at U, it should produce the image at V. Therefore, this figure results, and we can write the lens equation once again. 1 by F equivalent equals 1 by V minus 1 by U, equation 4. From 3 and 4, say This is 3 and this is 4. Right hand sides are same from the definition of equivalent lengths. So left hand side should be same. 1 by f equivalent 1 by f1 plus 1 by f2. This is how we derive the formula for equivalent focal length. So there we conclude this session and we proceed further in the next session.